Share screen 2. Syllabus. Okay, so let's do this. Everything's online. Classes from 2:30 to 4:20. Labs are at home. Same book. The intended outcomes are also the same. About how chemistry has impacted your everyday life, critical thinking skills, using math that you learned a long time ago. Communicate. This collaborate thing, it's probably not really going to happen very much this quarter because we're, distant.
Yeah.
And then we need, actually probably need more of this critically evaluate scientific sources of information since the president keeps saying that drugs that are supposed to help don't help.
Hmm.
Hmm.
That couple in Texas killed themselves about 5 hours after he suggested that could be a good drug. They
Oh.
ate aquarium cleaner
Oh my God.
because it had quinine, a compound of quinine in it. Okay, so since we're not meeting, I'm expecting everybody to log into Moodle several times a week. Turn stuff in on time on Moodle. No extra credit, grades. You guys know what those look like.
Mhm.
I think this number's wrong. I think this is 19. Still 3 exams. I think.
There will be 40 questions on the exams, right?
Yeah. Thanks for reminding me. You guys are the paper this time is gonna be about a molecule that does something inside of your body.
Okay.
So it's got to have biological, some kind of biological impact. Lots of things to choose from. So same situation, post it, and you're the only one that can do a paper on that. Same situation, 10 quizzes. Make sure that you know, be safe when you're doing your pretty safe labs at home. So we're gonna talk about acid base, and then we're gonna do aqueous, and then we're gonna do exam, and then thermo, electrochem exam, and then nuclear and organic an exam, and that's it. Knock this out in 10 weeks. You can bail by Friday and get your money back. And don't cheat if you guys know all this stuff. All right. Any syllabus questions? Take that as a no. Now what am I doing? Stop sharing the screen. Where are the notes? Oh, I know what we have to talk about before that. The labs. So somehow UPS put us on a do not deliver list. And so when we were getting deliveries, by us, I mean the college, and when we were getting deliveries, they were getting sent back to the shipping, whoever shipped them to us. So we were supposed to have all the chemicals ready for this labs 10 days ago, and they're supposed to show up today instead. So we don't have them. And the plan is if they show up today, that they'll get taken over to the Hood River campus, and I'll put the kits together, and then we'll figure out a time frame where I can pass them out. So what'll probably happen, I'll verify that everything's going to be there today, so I can do this tomorrow, and then if that's the case, I'll put up a doodle. It's just a thing that you say if you can or cannot make certain days and times, and then when we have enough people or everybody that can meet on the same day or time, then we all meet. So I'll probably just put all the kits in the back of my truck and then be at like the DMV in Hood River or something like that. And then you guys can come down and just grab them and bail. That way we don't have to infect
Do
each
the
other.
kids cost money?
No, the kits are part of your lab fee.
Cool.
Let's see what else with that. So expect to see a posting asking when you can meet up, and we'll take care of the labs that way. All right. So acids and bases. Okay. So when many people think about chemistry class. Acids and bases come to mind along with like blowing stuff up. Share those notes. And you know what? I don't want to do this. Sorry, just a second. I want to open up Note instead so I can draw on it. New page. 123 sid base. And then drag. Insert as a printout. What? There's nothing wrong with that. Open with. Open with. Note 1. What the hell? All right, I guess we'll be. Maybe I could print it as a PDF. Desktop, assets and bases. Desktop. Notes as and base. Insert as a printout. I guess it's a big file, so it's taking a little while to open.
Notes and acid and bases.
Yeah, notes for acids and bases.
When I printed it, it was pretty big too.
Yeah, there are a lot of images in it. Go here, share, note 1, share. Okay. Are you guys seeing the acid base times now?
Yep.
Ready. Okay, so when you think about acids and bases, what comes to mind? pH. Okay. We'll learn what that means. Anything else?
I always think of like vinegar and baking soda.
Okay. Vinegar and baking soda, acid and base, and you can get a nice reaction out of that. Anything else?
H's in front of the acids.
H's in front of the acids. Good. When you're naming things, you're looking for those H's, with the exception of what?
The CH. Acetic acid?
Acetic acid, yeah. Because it's CH3COO, and then the H at the end is the acidic one. Anything else? Nobody wants to say blood of aliens?
What was the
No.
xenomorphs?
You know, like the Aliens movies, their blood is quite
It's
acidic.
blood.
Or maybe
It's like
that
super acidic.
when you throw up, you it hurts.
Mm-hmm.
Stomach acid.
Or trying to shotgun a Coca-Cola, kind of painful.
That really hurts.
A lot of acid there. That pain is the back of your throat dying. All right, so we didn't know what they were. We've known that there's something associated with that because like vinegar has been around for a very long time. So we knew that there was some substances that we could eat and they had a certain kind of flavor to them. And they would do certain things. There's been acidic etching for, I don't know, at least 2,000 years, maybe 2,500 years. So we understand that there's something going on with them. But the first person who came up with a legitimate scientific idea for this, his name is, or I always say Arrhenius, but I guess it's something much more harsh, like Harinius or something like that.
Arius.
Beanie?
No, it's like there's some hard consonant sounds inside of there, and it kind of sounds like
Arrhenius.
no. I mean, it's like there's more a bunch of like in there.
Alright.
There's more phlegm.
Yeah. I had somebody who was from Ukraine in my class like 3 years ago. When I said it in class, she just laughed, and I'm like, "Okay, you pronounce it," and she did, and I'm like, "I can't say that." So he's Swedish, Norwegian, Finnish. I think he's Swedish. He's from a place where Vikings came from,
Mhm.
and his theory is called the Arrhenius theory. And what he said was anything that increases the H plus ion concentration. Can I draw on this? Anything that increases the H plus ion concentration in water is an acid. And anything that increases the OH minus concentration in water, that's a base. So why is hydrochloric acid an acid? Because when it goes into water, it disassociates, and I get an H plus floating around in the water. And why is sodium hydroxide a base? Because when sodium hydroxide goes into water, it separates, and I get OH minuses floating around inside the water. And so when you add an acid to the water, the H plus concentration goes up, the OH minus concentration goes up when a base is added to the water. And this theory is good. It's not good enough, but it's good. And I'll probably, when people talk about acid-base theory, almost invariably, they're going to be talking about the Arrhenius theory, which is usually fine, but not always fine. It doesn't describe some things, and it's imperfect. So Arrhenius, first guy, came up with stuff. He was actually trying to find dye when he realized what was going on. So as a chemist, one of the things that you can do that's very lucrative, at least during this time, was come up with different colors to dye clothing. Does anybody know what color he was trying to make?
Purple?
Purple?
Purple. Why purple?
It's really rare.
Purple's really hard to make. They use like snails in
Yeah.
the sea.
So it was difficult to attain a dye that would permanently dye clothing, specifically cotton and wool. And so purple was the royal color because the only people rich enough to get purple dye were royalty. So he was trying to, make purple available to the masses. And he was doing this with cabbage.
Actually, that's pretty smart.
There's purple cabbage, right?
Yeah.
So he was
Yeah.
trying to figure out a way to extract the purple out of the cabbage and color fast it to fabric, when he actually discovered something much more important, which is this theory of acid and bases. So if you've got a purple cabbage and it's in the presence of an acid or base, it will change colors. So if the purple cabbage is in vinegar, it turns one color. And if you saturate it with something that's a base, like I wouldn't suggest using Drano, but you could as a test, the Drano itself would actually, it would take the purple color away and it would become colorless. So in doing this, he disbanded his idea that he was going to make a dye and just started going with the acid-base theory, disseminated that across Europe, and then we all humans sort of understood acids a little bit better. All right, so again, this isn't a perfect definition, but it's a good definition, and it's one I'll come back to. But we're going to have to upgrade it a little bit, and we're upgrading it because there's problems with his definition. And so the next theory is called the Bronsted-Lowry theory, and I can only think of a couple of times when this happened, but Lowry and Bronsted didn't work together. One was from Denmark, one was from England, and this theory gets named after both of them because they both proposed a theory the same month in two different journals. So, and the theory was the same. And so nobody like scooped the other person because the information came out at the same time. So they just decided, Let's just name it after both of them. So they did. So the next better theory is called the Bronsted-Lowry theory. So the reason that I needed a Bronsted-Lowry theory is this thing right here cannot float free in water. Does anybody want to guess why?
Because it's a gas.
It's not a gas, it's an ion.
Does something
yeah.
with the hydrogen bonds between the water molecules?
Here I am, a water molecule, right? And this side of the molecule over here is partially negative because of the polarity. And I've got 4 electrons on this side of the molecule. And so what you're telling me is this H with a full-fledged +1 charge isn't going to be attracted to that? It is. So this thing here doesn't exist in water. But I'm going to write it, and it's going to be in the notes, and it's going to be in the book. And if you Google acids and bases, you're going to see this written again and again and again. So, sorry. I don't have anything else to say about it because it's just the way it is. Even though it doesn't actually exist, this is the way it is displayed, even though it's technically incorrect.
Okay, so that
So-
H plus.
When you see this H plus, you need to think this.
Ooh.
Oh.
So when somebody
That
writes an
makes
H plus down or says hydrogen ion in water, your brain just immediately converts it to hydronium ion, which is what that H3O plus is called.
Okay.
So you know how people who speak English and Spanish very well, and they're talking to other people who speak English and Spanish very well, they'll flip back and forth between English and Spanish, and neither one of them cares and probably don't even notice. For one reason or another, that the one word makes more sense to say. So I want you in your head, when somebody says H plus, to just don't even think about it. Immediately swap it over to H3O plus, because that's what's really going on. So Bronsted-Lowry said, hey, Arrhenius, thanks. This was awesome, but H plus couldn't possibly exist free floating in water. So we are going to modify your theory, and we're going to say that it turns into a hydronium ion. They also made a distinction about the water molecule where Arrhenius said that water can auto-ionize, meaning the water molecule will separate into H pluses and OH minuses all by itself. There's no reason for it to do that. If I wanted to pull a H plus off of a water molecule, I mean, what do you need to do? What would that require?
Boiling, adding energy.
Not boiling, but you'd have to add some kind of energy to get that done. And this is happening, we know it happens in all water at all times to a very small extent, and I don't need any input. So what they said was the reason that the water molecule auto-ionizes is because 2 water molecules run into each other with the correct orientation. So remember all that stuff about chemical reactions happening? So if
be aligned.
so if the water molecule, one of these water molecules' hydrogens runs perfectly into the other water molecule's oxygen's electrons, this hydrogen over here can get plucked off, and I have this, which leaves behind a hydroxide molecule. So for Bronsted-Lowry, like, this is an acid, and this is a base. So it didn't really change the acidity of the water because I've got one acid and one base in it, but I did disassociate the water molecule. So this auto-ionization occurs to a very small extent. Pure water actually auto-ionizes, and it's in the 7th decimal place, but it still happens. All right, so they renamed what the definition of an acid and base is. And so what these 2 guys said was, anything is an acid if it donates a proton. So what do I mean by a proton? Well, what's that thing right there?
An ion.
This is the proton.
It's just a proton, right? If a hydrogen atom is one proton plus one electron, and I take away the one electron because now this whole thing's got a positive charge, what I'm left with is that. So an H plus is a free floating proton, which is why when you have like a cut on your tongue and you drink some orange juice, it hurts like hell because it's very small and it gets right in there and attacks the nerve ending. Okay, so anything that gives away an H plus is an acid, and anything that accepts the proton, that thing is a base. So let's go back up here for a sec. So this water molecule accepted an H plus, and this water molecule donated an H plus. All right. So this guy here is my acid, and this guy here is my base, because this one has more H pluses on it, so it accepted it, and this one here gave away one of its H pluses, so it's an acid. So the acid-base reaction happens automatically without autoionization between water molecules, but it's actually a lot easier to see with something like this. Yay, Jeff's here. Hi, Jeffrey. Okay, so what's this substance right here?
Nitrate.
Nitric acid.
That's nitric acid, and then this is a water molecule. So which of these two things is the acid in this reaction?
The nitric acid.
The acid. Okay, great. So here's my acid. And why is this thing an acid by Bronsted-Lowry standards?
Because it gives away, or
Yep.
yeah, because it gives a proton.
This H right here goes over to the water molecule. So this is an acid. And so the water molecule is a base because it goes from having two H's, to having three H's. So it accepted a proton. So it is a base.
So whenever we say like a proton, is it always just going to be an H?
Yes.
Okay.
Yeah. When we're talking about acids and bases, if we're talking about isotopes or something nuclear, it's different. But in this case, we're specifically talking about acids and bases. Well, hold up a sec. You said H. That's not actually an H. It's an H
ion.
plus. Yes. Okay. H plus. Okay. So here's another reaction. That's Bronsted-Lowry. So this is ammonia and a water molecule. So who's the acid and who's the base?
It looks like the water molecule is the acid.
So the water molecule had two H's, and over here it's missing one of them. So now it's the acid. And then the ammonia becomes ammonium, so that makes this the base. So these lone pairs of electrons pluck that H off of there, and I'm left behind with ammonium and hydroxide. Does that make sense?
Yes.
Anybody else? Questions with that? No? All right.
So I have a question.
Go for it.
If water can change what acidity it is in this, is it completely dependent on what it's being presented with?
100%. So the water, remember when we were talking about what carbon does with its electrons?
Yeah.
Ethan?
Yeah.
So if the carbon interacted with the lithium, it would accept electrons from the lithium. If the carbon interacted with the fluorine, it would give fluorine its electrons. So the water molecule is the same way. If it interacts with something that really wants an H, it gives it. If it interacts with something that wants to give away an H, it accepts it.
Okay.
It's sort of amorphous in that matter. Okay, so here are a couple other reactions. So here's a hydrobromic acid and sodium hydroxide, and on the other side, I take this H off of the Br and I attach it to the OH that was on the Na, And so then the hydrobromic acid is obviously the acid, and the sodium hydroxide in this case has to be the base because it accepted the H. And I'm left with the salt and water. And if I've just got H plus and OH minus, I end up with the water molecule. This is the net ionic equation for this reaction. Why am I saying that this is the net ionic equation, the H plus OH equals water?
Because you don't have all the other stuff in it, you just have the stuff that changes.
Okay, so the reason that the other stuff didn't change is because the HBr is shown as aqueous. So that means the H and the Br are already disconnected. And the Na and the OH are aqueous, so they're disconnected. And on the other side, I've got an NaBr that's aqueous. So the Na at no time is connected to anything else, and the Br at no time is connected to anything else. So what do we call those things?
Spectators.
Yeah, so the sodium and bromine were just spectator ions in this reaction. The overall reaction was that we created a water molecule. That is a really common theme for especially biological chemistry. If a water molecule can be made, it's made. That is a driving force for chemical reactions within the body. All right, so we've got the Arrhenius theory, or the Norwegian theory, which is H pluses go up in water, and that's an acid, and OH go up in water, and that's a base. Then we've got the acid is something that donates a proton, and a base is something that accepts a proton. And now we've got a third theory, the Lewis acid-base theory. So this guy
It's the
was
same Lewis.
same Lewis, yeah. So second time you've heard his name, or third time you've heard his name. You'll hear his name again later. He was kind of a sad person. He had several grad students win Nobel Prizes, and he never won one. But I can't name any of those students that won Nobel Prizes because their work was too specific, where Newton's work was like an overriding chemical process. And he kept losing out to people who did really important things like Pauling discovering hybrid theory of carbon atoms, that kind of stuff. So he actually ended up killing himself in a lab
Oh,
because he was so
God.
sad. Yeah. So he, I need you to read this paragraph right here. This one that's quoted, and it says, "We are."
this just sounds like the Swedish one. Or
No.
like he's making fun of the Swedish one.
No, he's not making fun. He understands the validity of both Arrhenius and Bronsted-Lowry, but what he's saying is we have a huge classification of chemical reactions, or a huge like group of chemical reactions that we don't classify correctly. We're classifying them as like a redox reaction or something when actually they're just acid-base reactions. But because the chemists of the planet are thinking, I need water for an acid-base reaction, they don't see a reaction that is an acid-base reaction as one because it doesn't happen in water. And let me give you an example of one that you did. Do you remember this reaction?
Sort of. Oh yeah, where we tilted the things together.
You had two test tubes, right?
Yeah.
With liquids in them.
And then like a stuff appeared at the top of one of them.
Yeah, then you saw something. So if you can see it, that means that's not a gas. It's actually a solid. So you had ammonia coming out of here as a gas that you couldn't see, and hydrochloric acid coming out of this tube that you couldn't see. And when they ran into each other in the air, does anybody remember what the combination reaction produced?
Oh God.
It's a solid, and it's a
Yeah.
combination reaction.
Oh, then
Go ahead.
I'm trying to think.
Just put them together.
The nitrogen
I-
chloride.
Then it would be like ammonium chloride, I guess,
Okay.
right?
because NH4.
I just take this hydrogen and make it a 4 and then stick the chlorine to it. So what you were seeing in the air was ammonium chloride salt that was just produced. Is there any water present?
No.
No, it was in the
Well,
air. So this wasn't an acid-base reaction, when actually it is, because what happened? This hydrochloric acid gave the ammonia its its hydrogen, and then this was a positive and this was a negative, so the two things stuck to each other electrostatically. But nobody classified this very obvious acid-base reaction as an acid or a base because it happened in the air. So this is something that Lewis wrote and then disseminated in the early 20s, and then took a while for people to understand what he was talking about. But eventually, they decided that this is correct and this is the best definition for an acid base that we could possibly have. And so there's a bunch of other stuff that's I've quoted in here that he said that makes his definition the best definition. And when we get down to it, the 2 points that he's making are no hydrogen atoms are needed and no solvent is needed. Up here, we had no solvent, but we did have a hydrogen atom. But he's saying we don't even need the hydrogen atom. It's fine if you do, but you don't need it. So the cool thing about Lewis's acid-base theory is he's saying that all these other acid-base reactions that we had up here are still acid-base reactions because they still fit his theory. What we had was Arrhenius had a small number of reactions, and then Bronsted-Lowry made the number of reactions bigger that were classified as acid-base, and then Newton was making them huge. So now I've got a huge classification of reactions that I'm going to call acid-base, and that made things a lot easier for a lot of people. So, go ahead.
According to Lewis, then what is required for it to be an acid-base reaction?
There you go.
Oh, it's just okay.
So
it's just an electron, not even just H, not hydrogen.
So let's look at this one. So this proton would be attracted to those electrons. So the water molecule is donating a pair of electrons. And what's this H plus doing?
Taking it.
Accepting it. So you're the acid and you're the base. So it's not the hydrogen that's important. The thing that's important are the electrons, which totally makes sense because what's our definition for chemistry?
Electrons doing stuff.
Electrons doing stuff. And so electrons are doing stuff. Electrons are making a chemical bond, and we're done with this. We've got a hydrogen or a water molecule with a couple of electrons, a hydrogen, and a hydrogen, and then a plus charge. I'm not sure. Can you guys see? What do you see in the right-hand side of the screen?
Your drawings.
You don't see me, Gage, and a husky?
Yeah, I see you, Gage, and a husky.
I see you.
Oh,
I
no
don't see
husky.
Gage and a husky.
There's a husky. Oh.
Interesting. I wasn't sure if when I'm sharing a screen, if these little images show up or not, but evidently
Yeah.
they do. How
They
about
just
I
moved
haven't
the
seen
right
a single husky.
how about
They're
now?
through Zoom. I don't see them through your screen share. It's
Oh,
through
you see them
Zoom.
through Zoom. You don't see them through the screen share. Okay, that makes a hell of a lot more sense to me. Good. That because it's annoying me because it's covering up part of my screen.
No, I see your whole screen.
You want to see the husky? There's like little arrows on the top and bottom. You can go to find them.
I'd rather see the notes. Thanks.
You can just drag it, the box.
Yeah, they should
around.
be like really minimized on the side of the sharing, like on the right.
Yeah,
Yeah,
I see that.
I
now.
see your entire screen.
Oh,
I'll show you a husky later, but not right now. Okay, so we'll say that all acid-base reactions are technically Lewis acid-base reactions. And then I can reduce a bunch of the acid-base reactions and say these are Bronsted-Lowry reactions. And then I can have a smaller pool of reactions that I could call an Arrhenius reaction. Or we can just say they're Lewis acid-base reactions and have all of those reactions available to us to discuss. And then saying that, what did I say earlier about the Arrhenius theory?
That it was specific.
Well, wasn't the Uranus the I know you said the hydrogen that was supposed to be aqueous wasn't actually real.
Yeah, I said something else about it though. Does anyone remember?
And something else.
I said that even though it's not really true, we're still going to talk about it.
Yeah.
We're going to act like it's true, even though the Lewis theory is more correct. Because sometimes it's just easier to think about an H plus floating around. And in essence, you end up with the same thing. It's just a hydronium ion floating around instead. All right, so what things are Lewis acids and what things are Lewis bases? So are you okay with anything that's a positive, any cation is a Lewis acid? Tell me why.
Because it'll then accept another electron.
If it's positively charged, then it can accept electrons. It has that ability. So how about the next one?
Well, yeah, because it wants to fill its valence, so it'll be.
So it'll
take
accept,
electrons.
right? So something like, sorry, I gotta let Litzy in.
So to me, this sounds like a lot of ionic reactions would also count as Lewis acid-base reactions.
Possibly. So this hole here on the fluorine wants that electron, and this hole on the fluorine wants that electron. So these are unfilled octet rules. So I've got an acid-base reaction making myself fluorine gas. If I've got a double bond and it's polarized, then the positive side is going to be able to accept electrons. And if I've got an expanded valence shell, so remember we were talking about phosphoruses and sulfurs being able to go past 8. So they can also be Lewis acids and bases. So then the opposite of that is anything that's a Lewis base is going to, any negative ion is going to be a Lewis base because it has extra electrons to donate. And anytime I've got unpaired shared electrons in my valence, I can form a reaction. I can donate those electrons away. Then the opposite side of the polar bond that's negative. And then anytime there's a presence of double bonds. So what did we learn last quarter about double bonds?
They're strong.
No.
It's
The
easy to
electrons
react
are on
with
the
them.
outside.
They're on the outside of the atoms, and so they're very accessible. So the electrons that are here, those are very available to do some other reaction.
The pi bonds, I think.
Those pi bonds, exactly.
Okay.
All right. All right. So I want to talk about this. No, can't do that. I want to talk about this one for a little bit. I just need some space. Space. Blank page, maybe? That's fine. So there's the Lewis structure, same Lewis structure for nitrogen. And nitrogen likes to form 3 bonds. So, I can throw up a hydrogen here and a hydrogen here and a hydrogen here. These lone pairs of electrons are a base. So ammonia is a base. It will pull electrons off of water or hydrogens off of water molecules. Go ahead.
I was just saying, you said the electrons in the pair are the base? Or like just those or the entire
Well, that's
molecule?
the whole molecule is considered the base, but those electrons, this pair of electrons is the reason that ammonia is a base.
Okay.
All right. Okay, so let me erase. Oh, that's terrible. Do you guys remember what this is a structure for?
No. It looks super familiar, but
Amino acid, right?
Yeah, it's the base structure for amino acid, the generalized structure, because this R dictates which amino acid you've got. So, what did we say these lone pairs of electrons do?
They make it a base.
They make it a base. And then what's this side over here?
The carboxyl group. The acid.
So, that H will actually auto-ionize itself, and you'll end up with the hydrogen on this side and this being negatively charged, which means you end up having amino acids. Oh. That have a positive side and a negative side, which makes amino acids very reactive. Are amino acids important?
Yeah.
Yeah, they're what proteins are made out of, and proteins do 90% of everything inside of your body. So I need to make sure that the amino acids, which are chains, are reactive. So that means either side of the molecule, over here or over here, can have amino acids attached to it. And the reason that it reacts so well is because it auto-ionizes itself. This nitrogen pulls the hydrogen off of this side over here, and now I've got a cation on one side of the molecule and an anion on the other side of the molecule. So anytime inside of anything biological, if I need a base, I don't have these things floating around. I can't have Drano floating around in the bloodstream or inside of a cell. So instead, I've got nitrogen molecules with who knows what attached to them, and a lone pair of electrons that's acting like a base. So acid-base reactions, with the exception of what happens inside your stomach, are exclusive to these nitrogen molecules, almost exclusive to these nitrogens that have this lone pair of electrons on them. So it provides all of the acid or the baseness inside your body to handle all the acid stuff that occurs. Let's go back over it. No, that's not what I want. Where do those notes go? There we go.
On the notes there, for the examples of the Lewis bases, the second one, did you mean of or? One or more?
Where?
The second
where your
one.
cursor is, where
Right there, one of more or one or more?
Oh, that's definitely an or.
Okay.
You don't see the R? It's right there.
there's an R there.
It's an R. Okay.
I have a question.
Yeah.
We know what acids like do to our body if they're not like in our stomach, they hurt. But what do bases do to like our skin or our body?
Same thing.
They still like hurt.
Oh yeah. I mean, would you drink Drano? Of course not. This is a
No.
stupid question. Same exact thing kinds of happens. So when people think acids are bad, bases are good. No, they're not. But what's our rule?
These
Oh.
the same people that get like essential oil stuff?
Yeah, probably.
Quick question.
Yes.
I got a pretty strong base on my skin once and it didn't hurt. It just turned my skin slimy and like came off when I rinsed it off.
Yeah, like
Um,
bleach.
Sure. That's not a very strong base.
Bleach is pretty diluted.
Let me share screen 2. We're gonna actually talk about that sliminess here in a second, but where?
I was wondering about that.
So this thing right here. What
Oh,
was
yeah.
what was that?
The dose.
Oh yeah.
Dose makes the poison, right?
poison.
So I hear people talking about dietary stuff, and they're like, "Stop eating acids." I'm like, why? Like, really? You want to stop eating citric acid? That's going to be a problem. Do you want to stop eating scorbic acid? Do you want scurvy? Like, no. But eating a bunch of acids can't change the pH of your body. If you eat it, if you breathed it, maybe. I mean, it absolutely could if you disabled your buffer. But eating it doesn't do anything. Your stomach is a more concentrated acid than anything you could get down your esophagus. Does that make sense?
Hmm.
How do you know that that's the case?
Well, if you've ever like vomited before,
If you've ever thrown up, you know it hurts a hell of a lot more than anything that you send down your throat. So for somebody to say, "Oh, don't eat that because it's an acid, and acids do bad things to you," you can be like, "My stomach is filled with acid. That's orders of magnitude more concentrated than whatever this thing is that I'm about to eat." Where were we? So, what was your question, Annika?
Oh, the what I said about acids and bases. I said does the do bases hurt?
Oh, do bases hurt? Yeah. So, the answer to that is could maybe, and the reason is what's the concentration? Like, how much of it are you actually taking? If you drink Epsom salt in water, it's a little basic, but you won't even notice it. But in the same way that if you drink, I don't know, dilute orange juice, tomato juice, something like that, that's an acid in it. Doesn't hurt, still goes down, no problem.
Mhm.
But if it's more concentrated, then of course that's not something you're going to want to do.
So it still does the like burn feeling that acids have?
Sure, if the concentration's high enough. I would not touch Drano with my hands. It would hurt immediately because of the concentration is so high. And bleach, the concentration of bleach is low, and usually you're not actually touching the bleach itself. You're touching like bleach water, which is even more dilute, but still bad stuff's going to happen. All right, so next thing I want to talk about is the difference between strong acids and bases versus not strong acids and bases. Do you remember when we talked about electrolytes?
yeah,
Yeah.
So what was the difference between a strong electrolyte and a weak electrolyte?
if it was able to dissolve water completely.
That's it. So when we say strong acid or strong base, we mean it fully disassociates. So when a hydrochloric acid goes into water, I've got H's and Cl's in their ionized form. There is no HCl floating around as a molecule inside the water. It is disassociated. And so you need to remember, isn't it listed right here?
What the rule list of
Just
Okay.
which ones there are. Why isn't that written right? They're listed in the properties of
you have a
acids.
strong acid list on the next page.
Yeah. So we'll go over that list here in a second. So all I need you to remember is if I'm looking at a strong acid or I'm looking at a strong base, that thing fully disassociates. So when the hydrochloric acid goes into water, there's no hydrochloric acid on the other side over here. When sodium hydroxide goes into water, there's no sodium hydroxide over here. Can you tell me why this fully disassociates?
Is it sodium?
Because it's sodium, right? So if I attach a group 1 metal to a hydroxide, that thing's just going to leave, and then I'm left behind with a hydroxide. So if this is a strong acid, which it is, when I get over to the other side, the chlorine is just floating around free, and I've got a hydronium ion. So Bronson-Lowry would say it's a hydronium. Lewis would say it's a hydronium. And remember, Arrhenius would have just said that's an H+, and that's not really true, even though sometimes it's easy to think about it like that. So if let's talk about concentrations for a sec. If I made a 2 molar solution of hydrochloric acid, I actually have 2 molar hydronium ion and 2 molar chloride. Does that make sense?
Yes. Yeah.
Because if this is 2 molar and this fully separates, then this is 2 molar and this is 2 molar because they completely break apart. We good with that? I'm not hearing a lot of yes. Let's say I had 10 NaCl molecules and I dissolved them all. What do I have on the other side?
10 Na and 10 Cls.
Yeah, that's what's going on here. So if I've got 2 molar this, and I know this fully disassociates, I end up with 2 molar this and 2 molar this, because none of this is left because it fully disassociates.
Okay.
That's not the case for weak acids and bases. Can anybody name a weak acid that we discussed last quarter? I know it was like a month ago, but
Citric acid?
sure, citric acid, but I'm not going to draw that one because it's big.
It's big.
Anybody remember a super easy one? We did a calculation with it.
Okay.
Oleic acid?
That hydrofluoric acid, right? So when we did this, it was in an equilibrium, and we said that it was made H pluses and F minuses, but this was like 1,389 of these, and one of those, and one of those.
Yeah.
The reasoning is because this is a weak electrolyte, or in this case, because it's an acid, it's a weak acid. So when I say strong, it just means fully disassociates. It means the arrow goes one direction. And when we say weak, we mean the arrow goes both directions. It disassociates, then it comes back together. It disassociates, comes back together. But it mostly stays stuck together.
Last quarter, I thought you said all reactions are doing that, like going back and forth to stay in equilibrium.
Yeah. Yep. Yep. So this one right here, there is a backwards arrow right here, but it's you need an electron microscope to see it.
Okay.
Right here. And this one right here, electron microscope, because it's so small, where this one is more like an arrow going that direction. Sorry, that's wrong. This one, at least you can see it. So there's like a arrow going that direction, and there's an arrow going that direction. So yeah, all of these aqueous reactions, it is a double-sided arrow, but it doesn't really matter for us in this case. So when we say strong acids or strong electrolytes, just consider the arrow going one direction.
All right.
So let's talk about some properties. And we'll start with acids. So they produce hydronium ions in water. Do you know what litmus is?
The what now?
No.
Litmus?
Litmus.
This right here.
Oh, litmus.
I know it's paper, or you can put onto paper.
It's put onto paper, sure. It's a dye from cabbage.
Oh.
And if the dye is exposed to an acid, it turns red or it stays red. If it's introduced to a base, it turns blue or it stays blue. Does that make sense?
Yeah. Okay. Litmus.
All right. Acids are sour. So anything that you've ever tasted that's sour is an acid. So hit me up with something that's sour.
Orange.
An orange. Maybe.
Lemon.
Lemon, more likely. Something else?
One of those stupid giant oranges that are not oranges.
Blood oranges. Got grapefruits.
Grapefruits. Oh.
Giant oranges that aren't oranges. Grapefruit. Good job.
They're really big and they look like they're oranges, but they're not, and they're disgusting.
gross.
All right, how about these things?
Oh yeah.
Oh yeah, Sour Patch
Forgot
Kids.
those
Like-
That's citric acid.
Those are ridiculously sour, right?
Not
They're
that
not
bad.
that sour.
All right, well, maybe not anymore, but when they first came out, they were like close your throat sour.
Oh well, like warhead
Oh,
Yeah.
or the lemon heads.
warheads suck.
Yeah, lemon heads used to be really.
Warheads are like toxic waste that was like ridiculously sour. I forgot.
Warheads
Toxic
are
waste.
super sour.
So I knew it was warheads.
No, toxic waste were pretty dumb.
Just talking
Yeah.
about them, I'm starting
Toxic
to like
waste is pretty
salivate.
bad. oh god, the ingredients ready for a horror show.
What do we got here?
Sugar, invert sugar, corn syrup, modified cornstarch, tartaric acid, citric
Alright.
acid, and just a bunch of dyes. It looks like.
The one
So-
of them blue.
So there's a bunch of citric acid and a bunch of tartaric acid.
Tartaric acid.
So these two acids together make this very sour. They used to have malonic acid in there, which made it even more sour.
Mhm.
How about let's look at something else.
You could look at warheads. What's invert sugar?
Inverted sugar.
Yeah, what is that?
Citrus soda with caramel color.
Coca-Cola.
Man, it's been a while since I've had a Coke.
It's pretty bad for you, you know.
Stop drinking Coca-Cola. Okay.
Okay, so there's citric acid in here. That's one of the natural flavors. There's phosphoric acid in here. What other acid is in here that's not shown?
Carbonic acid?
Carbonic acid from the carbonated water. So this has 3 acids in it. So of course, when you try to drink this very quickly, it burns the hell out of your throat.
I would thought the burning was from like the carbon, like too much.
So
resistance.
explain to me why this product that has 3 acids in it is sweet and not sour.
Because there's so much sugar in it.
Crap ton of sugar in it.
And you
There's
want
an
to
incredible amount of
anybody want to expand on that?
A high fructose corn syrup.
It's processed sugar, so it's
No. Biologically expand on that.
Um,
Sugar lock out your ability to like deal with the acid.
Sorry, say that again.
that would make it harder or more sour. She
Well, no, like if there's so much sugar, the concentration of the sugar versus the acid, there's more sugar. So wouldn't your body like interact with the sugar more readily?
Nope.
Is it the same thing like what they do with McDonald's salt where it's just smaller?
Nope. Nobody?
Because it's not sugar.
No, it is sugar. Taste buds.
yeah, I was gonna. Does it have anything to do with your?
The taste buds that taste sugar are the same taste buds that taste sour.
Oh, so they.
So what if you do a little bit of, remember the stuff we were talking about with enzymes?
Yeah, it does. It's a competitive.
inhibitor?
It's you end up competitively inhibiting the ability of your mouth to taste sour because you've got so much sweet there.
But soda water tastes so awful.
So soda water is delicious.
Oh
What are
no,
you
I
talking
use
about?
that like Epicac.
Oh, that's not soda water. That's first off, that's a poison.
No, I don't use Epicac. I mean, it does the same effect. It makes me really nauseous.
Yeah. Do you mean hydrogen peroxide?
No, I mean like soda water, like just.
What are you talking about? Soda water doesn't
Like
make you
bubbly
nauseous?
Like carbonated water, Gage?
I drink like
Well, it might-
5 of these a day.
Yeah, but it
No
might make you
vomiting.
nauseous. Things have different effects on people. Just because you're obsessed with soda water doesn't mean Gage has to like it.
Well, I'm not saying he has to like it, but it's not going to induce nausea, is what I'm saying.
It makes me nauseous.
I think if it makes him nauseous, it makes him nauseous.
All
I
right.
think that's a psychological thing.
I don't know why.
I think he just wants sugar, and it has none.
I mean, he doesn't use salted butter.
Weird.
Ugh, salted butter is gross.
What are you talking about?
What, you say salted butter's gross?
No, unsalted butter is gross.
Oh, I was gonna say salted butter's too salty.
Salted butter is too salty.
Because they just put like a salt lick on it.
Ethan,
Yeah.
does she eat regular butter?
I don't
I-
think
I can't
Ethan
answer
knows
don't
what
know
butter I eat.
All right.
I
Why
can't
do we-
answer that. How
Okay.
would
Why
you
would-
ask me?
I don't add salt to my food, Kovacic.
Okay, so when you go to the grocery store, you actually buy butter that says unsalted?
Typically, yes. The stick butter.
That's weird.
I do too.
It's kind of weird, champ.
Don't
Weird.
call me
Even.
weird, champ, Ethan.
Evens.
Anyways, can we talk about chemistry, please?
We are. We're talking about the oddity of the chemistry of your mouth and evidently Gage's stomach.
My God. Please.
Gage's odd stomach.
This is-
Considering
this is
soda water
fine.
is usually something that causes people's stomach to settle and make them not nauseous. Okay, so let's get back to the sour taste thing.
Yeah.
Because of sugar, you can overpower sour. So acids are in a lot of foods that we eat, and we generally enjoy them, but we usually like crush the overall sourness by adding sugar to it. So like sweet and sour pork, like how can you take that? There's a lot of acid in there because there's obviously a bunch of sugar in there combating the sour taste.
What's this? What's the acid in sweet and sour pork?
It's probably acetic acid.
Okay.
I don't like it, so I haven't made it, so I'm not sure. But acetic would be my guess. All right, so what other things do acids do? So we've got with a double replacement reaction with an oxide. So we can turn a rusting metal into a salt. A double replacement reaction with a hydroxide, that's just neutralizing a base with an acid, and so you're going to end up with a salt and water. Double replacement reactions with carbonates and bicarbonates or hydrogen carbonates, you end up with a salt and CO2. So that's the bubbling effect. If you were to take like a Tums and dribble Coke on it, it would bubble like crazy.
Mhm.
If you take a Tums and throw it into your stomach, then you're going to create CO2 and you're going to need to burp because you're going to be producing carbon dioxide in your stomach to remove the acid. And this is really important. If you take acid and you put it on almost all metals, but not all metals, the metal will dissolve and hydrogen gas will be generated. So if we want to refer back to the Aliens movies, the reason that they're able to like their blood dissolves like deck plates on ships is because there's acid in their blood. The deck plates are made out of metal, so it dissolves them, turns them into an oxide, basically a salt, and then hydrogen gas is generated.
What metals wouldn't be dissolved by an acid?
What metals do you think?
Like iron?
Not iron.
Like with titanium, cobalt, something like that.
No,
Tungsten?
no.
Corrode resistant.
So if somebody gave you a valuable piece of metal, what would you not want to happen to it?
They corrode.
So what when someone's giving you a valuable piece of metal, what do we call that?
What, precious metals?
What do we call the object? A
Oh.
gift. How about a coin?
Oh, like
Oh
copper?
yeah.
A copper coin or a gold coin or a silver coin? Why are they coins? We had this discussion.
Because they can't corrode.
Because they don't corrode when
They don't lose
the
value.
acids on your fingers touch them, or if you spilled some ketchup on your coin, you don't want your coin to dissolve, right? You drop your coin into a can of Coke, you don't want your coin to dissolve. It won't dissolve.
Is that why iron statues turn green? Or not iron I think it's
Copper.
iron statues? Copper statues.
Like the Statue of Liberty.
No, that's because of oxygen, not because of
Okay.
acids. But we'll talk about that another time. So this is the list of strong acids. This is the whole list.
Do we have to memorize it?
Well, it's a really short list.
Sorry, I'm not. Okay. Oh,
And then these three right here, what do they have in common?
They only have
Hydrogen
two.
and a what do you call them?
Halogen
Halogen.
minus hydrofluoric acid. And then, like, you definitely know hydrochloric acid, and then hydrobromic and hydroiodic go with that. Nitric acid, sulfuric acid, and then this is, what's the name of this guy?
Boric acid and chlorous acid.
No,
The hypochlorite.
nope.
Oh god.
Perchlorate, chlorate,
Per-
chlorite, hypochlorite. So this is chloric acid, which is different from hydrochloric acid, right?
Mhm.
And this is perchloric acid because this is perchlorate. So chloric and perchloric acids, and then nitric, sulfuric, hydrochloric, hydrobromic, and hydroiodic. Those are all the ones that are the strong ones. So there's zillions of acids in the universe, and only 7 of them are strong. So just remember the strong ones, and you don't have to worry about knowing anything about the weak ones, because if it's not one of these 7, then you automatically know it's weak.
Okay.
These are the concentrations that you can get these acids in their maximum. So HCl only goes up to 12, nitric goes up to 16, and sulfuric and acetic acid only go up to 18 molar. So if someone's like, I got a 30 molar solution here, you'd be like, that's not possible. What do you think happens if I try to shove more hydrochloric acid? So I got a bottle and it's got 12 molar hydrochloric acid in it. I try to shove some more HCl in there. What happens?
Or it's gonna turn to gas.
It just leaves as a gas. The way you get it into the acid in the first place is pump it in as a gas, and then it attaches itself to the water molecules and becomes aqueous. And then basically what we're saying is 12 molar is the saturation point for water molecules. Just like when I throw salt into water, it dissolves until all the water molecules are occupied. So I can't add more salt to water to make it saltier, and I can't add more acid to water to make it more acidic, because the water molecules have a finite ability to dissolve that acid. Okay.
What temperature is that 12 molar at?
Did you
I'm
say
pretty sure it's
temperature?
Standard.
Yeah, temperature.
It works at room temp.
Well, what I'm asking is like at lower temperatures, can you maybe squeeze a little bit more in there?
Wouldn't it be higher temperatures?
Gas is the opposite of solids.
Yeah, but this is
Like the physical
Like,
amount of
barely, like you might be able to go from the 12.1 to 12.11, but not really. It can't, the concentration doesn't vary that much with temperature. Do you remember the sodium chloride line on that chart?
Mhm.
Remember, it was basically flat.
Yes.
Same situation happens with the hydrochloric acid on the low end of the scale, and on the high end of the scale, as temp goes up, then it becomes less soluble.
Okay, thank you.
So it's sort of like a okay. Let's talk about properties of bases. So they produce hydroxides in water. They turn the litmus from red to blue. They feel slippery.
Can
So
you explain litmus again? I'm sorry.
The cabbage dye.
let me do this. Q.
Litmus is specifically to cabbage.
Just a second. Acid base.
Thank you, Allison.
That's not what I want. All right, where is that thing?
Thank you, Allison.
All right, 1 second. Oh, you know what? It's under. Ah, there it is. This isn't litmus, but the similar process occurs. So this is something called phenolphthalein. And so the phenolphthalein itself is colorless. And when it is in a base, when it's neutral or if it's acidic, and then as soon as there's excess OH molecules, then the shape changes and then the color changes to like a pinkish color. And the same sort of situation happens with litmus, except instead of it being colorless in another color, it's either blue or it's red.
Okay.
Do
So litmus is like a type of molecule?
or it is a molecule.
It is a molecule.
Good die.
So there you go. There's a litmus under neutral, litmus under red, litmus under blue, under a base. So do we see what's, let me open this in a new tab. What's changed from the top to the bottom?
In the bottom, the hydroxide has become a oxygen ion, and then in the top, there's been a hydrogen atom added.
Does this make sense?
Well, based on the first theory, it makes sense, but also,
Image.
well, I guess,
Let's go over here.
yeah, it does make sense because it's being given and shaking ions.
Oh, really? Why is that? All right. Let me screenshot. Control A, delete, Control V. All right, that's not going to work. Let's go to my favorite program, Paint.
Amazing.
Control A. Bum-bum. There. Right there. Control A, copy. Control V. Except now it's too big. So tell me about the water in a basic environment.
There's more oxygen ions present.
No. Oxygen? Huh?
The water in the base is probably going to be attracted to the oxygen.
No. In a basic environment, there's a whole bunch of OHs floating
Oh.
around. All right?
Oh,
So what are the OHs doing? They're grabbing these H's and turning into water molecules. So what does that leave? It leaves this molecule here, and this molecule is blue. But then the opposite, if I'm in a situation where there's an excess amount of H pluses, so here I am writing H pluses when really I mean hydronium, right?
Mm-hmm.
mhm.
So, hey, look, there's a lone pair of electrons right there. I'm going to attach myself. Oh, hey, look, there's a oxygen down there with a negative charge. I'm going to attach myself. And then I immediately turn red.
Okay.
We good with that?
Mhm.
Where was I? Here, here, over here. So we were talking about this slippery feeling. So
Yeah.
we've discussed this before. So can anybody figure out what I'm talking about with the slippery feeling?
The base interacting with like the oils on your skin
To make
makes like a.
Does it make like a? Well, does it have anything to do with myself?
it makes soap.
Cool.
So if you touch something that's basic, there is going to be an oil on your skin. And when the OH and the oil interact with each other, it makes a soap. So the slipperiness is what?
It's soap. That's like when we made the soap lab and we had to continue adding
Yep.
base to it until it produced the soap.
Yep. So you make soap out of yourself. Like when you touch bleach, the bleach is basic, and so you making soap out of your skin. So why is that, or not out of your skin, but the oil on your skin? So why is that? Why is that a bad thing?
You get the oil on your skin.
Dries out your skin.
So what is the oil on the surface of your skin doing?
It's like a
Protecting it
repair
From what?
from
from germs.
germs,
No.
oxygen,
No.
dirt,
Drying out.
from losing water.
There's water in, so if this is, if the air is out here and your skin is here and the water is here, there's an oil
What-
sheet on top of it. The water will not penetrate past that oil because one's polar and one's non-polar. We good with that?
Mhm.
So as soon as this oil disappears, there's nothing to stop the water from just simply evaporating out. And so then your skin cracks and then you bleed and bad things happen.
Just live in water.
Or just use
Put
chapstick.
cushion on.
I like being able to just live in a pool.
No,
First Hellboy movie.
you'll become like a prune.
There you go, Abe.
Abe, yeah. Sad that he didn't do the second movie.
The Matrix.
Oh, that's disgusting.
What?
Living in a fluid in the Matrix.
Yeah.
Ew,
fine.
ew, ew. Can we please talk about chemistry? Oh my god.
Okay, so they also taste bitter. So there's something interesting about the fact that the acids are sour and the bases are bitter. If you've got something bitter, you can't saturate it with sugar and expect not to taste the bitter. Why? Based on our prior logic.
Is there different taste buds?
The big,
Yeah, some people can't taste it.
the bitter and the sugar, they're not tasted by the same thing. So if you take an orange peel and, I don't know, covered in sugar and eat it, you're still going to taste the bitter of the orange peel. So we were going to do this lab, but we're not doing it now. To break down fats and oils, the household cleaners that you're going to use are going to be basic. So usually when there's something that needs to be cleaned, like on your stovetop, it's oil of some kind, maybe fat from like a hamburger or olive oil that splattered out when you were, cooking some asparagus or something like that. But regardless, on top of the stovetop, you've got fats. So it doesn't really work if you just get your sponge wet and then clean it because they're hydrophobic, and so the oil doesn't want to come off the stovetop. But if you spray it with a base like Formula 409 or a tiny bit of bleach, what do you do to the fat that's on your stovetop?
You just all
Break it down. Like soap.
You make soap, which is great because I was trying to clean stuff, right? So now I get to clean stuff. Okay, and we had the discussion about where we ended up finding soap before. So, and here's your list. Here's your whole list for strong bases, meaning all the rest of the bases are weak bases. So what does this list have in common?
they're all attached to a hydroxide.
What else did this list have in common?
Lithium, sodium, potassium.
Oh, they're all metals
Oh,
or one metal.
They're all
No.
They're all column number 1 off the periodic table attached to a hydroxide.
alkaline metals.
Alkaline metals attached to a hydroxide. So any of those things work well for like a drain cleaner. So now that we've talked about this, does it make sense that Drano is sodium hydroxide?
Yes.
What is it that's usually clogging your drain?
Oils.
Coagulated fat. So you send a strong base down, and what happens to my coagulated fat?
It just turns into soap. and
Turns
then
into
goes
soap.
down the drain.
And cleans it up. So then you want to add other stuff like something that'll be effervescent, so you can get the soap to move around and bump the coagulated fat and just get everything agitated. So sometimes aluminum is added with the base because then it gets a little bubbly. Sometimes you'll have those containers of drain cleaner where the substances don't touch each other until you actually put it into the toilet. Those work really well. And so since these are all strong bases, they're soluble. They go in, the group 1 metal drops off, and then the hydroxide's there. Okay. Next thing we'll talk about are properties of salts. So how do you make a salt?
Mix an acid and a base together.
So do we have a lot of, say, table salt on the planet?
Yes.
So think about the ocean. Where did it come from?
Where did the ocean come from?
Yeah.
A lot of asteroids. Icy asteroids hitting the planet really early on.
Anything else?
Well,
If that was the case, then the water would be fresh. A bunch of acid-base reactions that made water and salt. And when I mean a bunch, I mean giant atmospheric reactions. So really big things, obviously, since the ocean is miles deep and miles across. Many of the salts are soluble, but not all of them, because, I mean, we know that not all of them are soluble because we have that list of solubility rules. We use the fact that most salts are soluble to get drugs into the bloodstream. We had this discussion before about, say, like naproxen sodium. That's Aleve. And so the Aleve, basically the polyatomic ion is not soluble. So they had it, they reacted it with a strong base and then turned it into a salt. And then you ended up with a salt so that when the sodium hit the water, it let go, and now everything is solubilized. The other name for salts is an ionic compound. And we're going to talk extensively about this next thing, which is salts of a weak acid and base are used to form buffers. And so there'll be a bunch of calculations we do with that for this, this set of notes. And then the last thing is salts can be hygroscopic. And we've talked about that gypsum stuff before when we were talking about drywall. And so not all salts are hygroscopic, but most are. And the
what do you
level
mean by hygroscopic?
Absorbing water.
Oh, okay, cool.
So table salt left out becomes rigid. At least the surface does, because it's absorbed moisture out of the air, and there's one water molecule attached to the table salt, and then that makes it not granular anymore.
Mm-hmm.
And so the same thing happens with calcium sulfate. If I allow two water molecules to attach to each of the calcium sulfates, I get that gypsum stuff. And so that's our drywall. Yeah. Okay. Let's see what else we got. Do we want to talk about anything that we've discussed so far? Any of the three theories or properties?
Are we gonna go over more properties of weak acids and bases?
Yeah, that's going to be a
Later.
whole section of weak acids and weak bases where we do lots of calculations and lots more calculations. I think I'm going to call it good. We're going to stop here at polyprotic acids. We can pick up again next class.